Hello again, everybody. This is the third recording for this week for game theory and optimization. And the topic of this mini lecture is auction design. So it's one of the applications of Bayesian games. And so it's the auction design is, of course, very heavily used in economic theory and also in economic practice. It's in fact one of the success stories, you could say, of game theory in real life. But what we are going to do is to look at a relatively simple model, actually one of the first models that was ever studied, and see how the analysis using Bayesian Nash equilibrium can help us to tackle this economic problem, because there is an underlying economic problem behind the auctions. So the model that we're going to look at is the first price sealed bid auction with n bidders. And like I said, there is auctions are a cure to a problem, you could say, and we're first going to explain what we are actually trying to solve here. So the setting is as follows. There is one single indivisible item for sale. So that is already something fairly specific. Most auctions, at least the ones that are used in economic settings, allocate lots of items simultaneously. But here we keep things simple. We're going to look at a situation where only one item is for sale, and it cannot be divided among the agents. So you can only assign it to one person. And there are n persons interested in this item. So you have n possible ways to allocate to person 1 or to person 2 or to person n. There's one alternative option that is not to allocate at all, but for the moment we're not going to consider that one. And so what is now the problem? The problem is that each of these bidders has a valuation for ownership of the item, and that valuation is a number between 0 and 1. That's also to keep things simple, or at least to normalize it, and that is, you can think of it as the willingness to pay. So how much is it worth to that agent? And that valuation is denoted by VI for bidder I. These valuations are private information, meaning that bidder I knows his own valuation, VI, but he has no information regarding the valuations of other bidders. And in particular, also the seller, so that is also called the social planner, in economic theory, does not know any of the valuations. Valuations are IID draws from the uniform distribution on the unit interval. So that means that the draws are made independently. That's the first I. And the second I, together with the D, means identically distributed. And that means that they all come from the same distribution. In this case, the uniform distribution on the interval from 0 to 1. So this is the setting, and what we want to do is now to allocate, and we want to allocate in a very specific way. You have to think of a social planner, so let's say a government who wants to solve this economic problem, so they have a certain item that they want to license for, so a very popular application was, for example, for mobile telephone networks, a license to actually build a network. And typically the government wants to allocate efficiently, which in this case translates into allocating the item to a bidder with a highest valuation. So the VI should be at larger or equal to any of the VJs for other people. If there happen to be two people with the same VI with the same valuation, then you can simply allocate to one of the two, and both allocations will then be fine, so you can choose. But in general, of course, there's only one maximum, and then you have to allocate to the bidder with the maximum valuation. So this is the task. And is this a difficult task? Well, if you would know all the valuations, of course not. Then you can simply communicate to the one with the highest valuation. You know who that is, and you can strike a deal. However, the problem here, as in many economic problems, is the information asymmetry. The bidders only know their own valuation, and in particular, and you could say crucially, the seller, the social planner, the government, if you wish, does not know any of these valuations. So they want to build a system, a market or a trading platform or whatever, and in our case, an auction, in such a way that if these agents participate in that auction, then automatically, by workings of the mechanism of the auction, allocation turns out to be efficient in the end. That's what we want to achieve. We want to build a model in which this happens. And can we do that? And the answer is luckily yes. One way to do that, there are many, or at least there are more ways to do this, but one of them, and the one that we're going to look at today, is called the first price sealed bid auction. So how does that work? It works in 3 stages. So any auction always has 3 stages. Maybe that's a good thing to write down explicitly. Building an auction always has these 3 ingredients. First of all, you have to specify what bidders can do in the auction. So what are the possibilities? Can you only make 1 bid, or can you repeatedly bid in the auction, or do you have to, I don't know, hand in some documentation? Can be many things. And then based on these strategies, so based on what people did in the auction, you have to make 2 decisions. The first one is to allocate, of course. In this case, 1 item, and you have to say to who you allocate. But in general, that can be more decisions if there are more items to allocate. And the third thing to specify is payment or payments. In this case, there's only going to be 1 payment because there's only 1 item. But in general, you could think that more people get something in the auction, and then more people might have to pay. Maybe a good thing to mention, in this case, if the payment is PI for agent I, then his net utility is, if he gets something at least, of course, VI minus PI. So if you get something, then this is your net utility. And if you don't get anything and you don't pay anything, then it would be 0. So in this case, these are going to be the 2 options. Either your utility is VI minus PI or 0, but we'll get to that in a second. Good. So these are the strategies then. Each bidder has to submit a bid. That's a number between 0 and 1. And the interpretation of that bid is indeed, this is what I would maximally want to pay for the item. Bids are made simultaneously, hence the name sealed bid. You can think of all the bidders putting their bids in an envelope and then handing them over to the auctioneer, who then will open all the envelopes and see who is the winner. And how is the winner selected? The one who gets the item, that's the one with the highest bid. So you can think of this as a kind of replacement of allocating to the one with the highest valuation. That is what you would want to do, but you can't because you don't know the valuations. So instead you let people submit bids, and then you allocate to the one with the highest bid. And so that's the one who receives the item. There's only one item, that's all we can do. And that is then all that happens. The other ones get nothing. And well, that's why it's called first prize. The winner, the one who is allocated the item to, pays his own bid. That's why it's called first prize. And all other bidders pay nothing. And that's it. So this is the entire description of the first prize sealed bid auction. Yeah, so and this is an application of Bayesian games. So maybe the first question is indeed, can you actually see this as a Bayesian game? The answer is yes. So maybe you have to think about it for a second. But for example, the bidders are of course the agents, and the types are the valuations. So these are the type space is now not finite. But it's an interval, and so and the realization is a VI instead of a TI. The action spaces are again from 0 to 1. So this is the bit, you could say. So this would be VI and this would be BI. And yeah, the utility, that's what I already said. If you're the winner, and this is your utility. VI minus BI, the net profit, you could say, your gain, your valuation minus the payment. And otherwise it's a 0. And the prior, that is given by the uniform distributions over all these intervals. And so you have on each TI, for each TI, you have a draw from the uniform distribution, and then the distribution over profiles is simply the product of all these probabilities. Okay. I hope this is clear so far. So we can see this as a Bayesian game in this way, and that means that we can also talk about Bayesian Nash equilibrium. And my claim is that this bit strategy over here, so a strategy now is for every possible realized type. So in this case, for every possible realized valuation, VI, you have to specify your bit. And how do we do that? Well, we're going to look at this particular bit strategy where the bit for agent I, if his valuation is VI, is equal to n-1 divided by n times VI. So you bid a fraction of your valuation. If there are 2 bidders, so if n is 2, then you bid 50% of your valuation, and then n-1 divided by n is a half. If there are 3 bidders, you bid 2/3 of your valuation, etc. There are 4, you bid 3/4, and so on. So you have to know n. N is collectively known. That's the assumption here. You know how many people you are facing in the auction. Otherwise, you can't do this. But we assume that you know n. Okay, and the claim is that if everybody uses this bid strategy, that this is then a Bayesian Nash equilibrium of the game that is represented by the first prize sealed bid auction. And that's what we're going to check. By the way, notice that you do not really bid your valuation itself. In the first price sealed bid auction, that is typically not a clever thing to do. Because if you don't win, then if you would do that and you don't win, then of course your utility is 0. But if you do win, then your utility would be the valuation minus your bid. And if you bid your valuation, then that would be your valuation minus your valuation, and that's also 0. So that means that bidding your true value, the VI, would guarantee you a payoff of 0. And hopefully you can do better than that, of course. Okay, so we're going to check this particular statement. And I think what you need to get away from this is, in particular, the way that we check whether or not something is a B&E. That is an important thing to learn here. So how do we do that? How are we going to check that this strategy profile is a B&E? Well, you put yourself in the shoes of one of the bidders. So you think about being bidder I, and you know your valuation. So this is an interim solution concept. So it's not ex ante that nobody knows the valuations. It's also not ex post where you know all the valuations, but this is interim. You know your own valuation, but you're still going to take averages over the realizations for other agents or other bidders. So you know that you have valuation VI, and you also know that the others are going to bid according to this strategy profile. So that is the Nash equilibrium part of it. You fix the strategies of the other ones, and then you're going to check whether you bidding like that as well is indeed a best response. That's what we're going to do. So you assume that the others bid according to this bid strategy. Of course, you don't know the VJs, but you do know that for each bidder J, if he has a certain value VJ, then this is how he constructs his bid. So that is what you do know. So you do know that this is how opponents construct bids given their valuations. So this is what you know, and now what you're going to do is you want to find a profit maximizing bid. How are we going to do that? So this is the information. Now we want to find the best bid, the best response, you could say in game theory terms. How do you do that? In 2 steps. First, we're going to simply compute, well, simply, that is a lot of work, but we're going to compute the expected payoff given a certain bid. So you simply fix the bid B between 0 and 1, and we're going to compute the resulting expected payoff. Once we have that, then we have a function that depends on B, and then we can maximize the function that we find over the bid. But the first step is simply just take any bid, compute the expected payoff that is associated with that bid. So that's stated over here. What we want now is to check that indeed is bidding like this, bidding n-1 divided by n times VI, maximizing this expected profit over all possible bids. So we take one bid, and we're going to compute this EI VI B. And so this is the information that we had, and now we're going to compute this expected payoff, given that I know that my valuation is VI, and given that I bid this bid B between 0 and 1. Okay, so how do we do that? Well, this EIVIB, how does it look like? Well, it is given by this formula on the right-hand side of the equality sign. If I win, then we already saw that my net utility is VI minus, well, it's a first price sealed bid auction, so minus B, minus my bid. So I know my utility if I win. That's simply VI minus B, so stated over here. this to work. No, that's not what I wanted to do. This over here is my utility in case I am the winner. And so I want to have the expected payoff. So then I need to multiply that by the probability that that is actually going to happen. And that's what is stated over here. So the probability that in fact the bid that I submit is the winning bid. This I know, right? I know my valuation and I know what I'm bidding. The only thing that I need to compute is this probability over here. So that's what we're going to do. Yep. So how do we do that? Well, when do I win? I win if my bid is better than any of the other bids. So I want to compute the probability that my bid exceeds any of the other bids. So all higher than all BJs submitted by J other than me. I write a strict inequality here, but that's because the probability that is going to be exactly equal is 0. So I can safely ignore ties. That's just a remark that I make now. This is something that you can actually check after the fact, but you can. That is actually the case. So I want to compute the probability that this is going to happen. And now what I know is that the bids of others is given, by this expression, right? So this is where this is the point where I'm going to use the fact that I know the bid strategies of other people. I'm going to compute the probability that my bid exceeds that expression over there. So I want to know the probability that my bid exceeds this expression for all j. So when that probability, where does the probability come from? So it's a probability, right? That's what it says over here, bro. And in what sense is this a probability? What is the thing that I do not know? Well, there's only one thing that I do not know, and that is this Vj over here, right? That's where the uncertainty is. So I'm going to rewrite this in terms of Vj. Namely, I want to have a probability that this is a random variable, at least as far as I'm concerned. I am I and not j. So for me, Vj is a random variable. And I want to know the probability that that random variable is smaller than this expression n divided by n minus 1 times my bid. How big is that probability? Well, that is something that's always good to understand. So I am considering a random variable Vj that is uniformly distributed over the unit interval. Now, what is the probability that such a random variable would have a realization, for example, smaller than 7/10? So what is the probability that my realization is within this interval? Well, it's a unit interval, so the total probability is 1 to get a number between 0 and 1. And it's uniformly distributed, so everything is equally likely. So the probability that that happens, the probability that Vj is smaller than 7 divided by 10 is, what is that? Yeah, that's 7 divided by 10. Right? And the same way, the probability that Vj is smaller than a half is a half, etc. So the probability that Vj is smaller than this number is, in fact, that number. So that makes it easy. So what I get here is now that this is going to be Vi minus B times, yeah, the probability that Vj is smaller than this is that number. By the way, this number here might be larger than 1 in general, if I because this fraction is bigger than 1. But again, after the fact, you can check that that is not going to be the case. So the optimal B will be in such a way that this is smaller than 1. That's again something that you need to check afterwards, but that's going to be true. So. Okay. So we have this, but that needs to be true for all j other than I. So this is just for one j, right? So what is now the probability that that happens for all j? Well, these draws from the Vj's were, if you remember, independent. So the probability that one of them is smaller than this number is that number. So what is the probability that now all of them are smaller than this? Well, that's simply the product of the separate probabilities. That's the independence condition. That the probability of the joint event is simply the probability of the individual events. And how many j's other than I are there? Well, not n, but n minus 1, because I don't count myself. And that's the expression that we were looking for. Like this. And you see now I have an expression that only uses things that I know. Namely, I know my own valuation, I know my own bid, and I know how many people participate in the auction. So now I have an expression that me being bidder I actually know. So we can maximize this over B. And that's what we're going to do next. By the way, if in the exam you get a question like this and you end up with an expression with a lot of Vj's in it, then you are sure that you did something wrong, right? Because you're actually averaging out over all the other Vj's. So that means that in the expression that you end up with, the Vj should be gone because you actually computed there. Right? That's what you averaged out over. So it should vanish. Okay, so we've got this expression. And now what we want to do is to find the maximum. So we're going to take the first, the derivative and set it equal to 0. So we want to look for stationary points of this expression. Yeah, how does that work? Well, you can check that this is the first order condition. Maybe I should briefly discuss this. So what happens is, of course, that we treat this as a product, right? And this first expression over here is actually over here. We have F. And this is the derivative of G. And so G is, well, something to the power n minus 1. So that is n minus 1 times that something over here to the power n minus 2, 1 less than n minus 1, times the derivative of what is between the brackets. You have to use the chain rule. And that is why this extra factor over here is present, because that is the derivative of this over here with respect to B. Minus, well, and then this is simply G. and sorry, it's of course plus initially, right? But the f prime in this case is -1, meaning the derivative of this expression here with respect to b. So that's why we get a minus over there. Okay, so that's this expression. That looks very, very impressive, but we can clean it up quite quickly. Maybe we should do that. The first thing that really helps a lot is to observe that this is it's a difference, right, between two terms. This is the first term, and this is the second term. And both terms have n-2 factors of the form n divided by n-1 times b in them. And so there are n-2 of them over here, and there are n-1 of them over there. So both of them have at least n-2. So you can throw out n-2. I simply divide by n-2 of these factors. That means that all these are gone. And here one of them remains. And the other thing I can do is then to multiply by n-. So this n-1 cancels with that one. And what remains is that n times vi minus b minus n divided by n-1 times b is 0. That already looks a lot more friendly. And what can you do with this? Well, you can actually try to solve this for b, right? We want to find the maximum bit, so we have to solve for b. Well, one more thing that you can do is to throw out the n. So what I have left is that this, in other words, this, right? You put all this on the right hand side, and then it reads like that. What is this saying? This is saying that vi should be equal to n divided by n-1 times b. And also 1 times b plus 1 over n-1 times b. And of course, 1 is the same as n-1 divided by n-1, and then you add one more. And now you again multiply. So you put this factor over here. You move it to the other side. So you multiply with the inverse. And then you read from right to left that b is indeed n-1 divided by n times vi, which is exactly what we wanted to achieve. That if my opponents bid like this, then it is the best response for me to use the same formula. That's what we see. And yeah, you can, if you wish, take second order conditions, check for maximum location. You can also make a sign diagram if you wish. And if you do that, you will see that this is indeed a maximum. Okay, so we now know that this is the Bayesian-Nash equilibrium. And well, so if you remember what we actually wanted to, this is of course nice, and this is 90% of the work. But the Bayes-Nash equilibrium is only a tool in the sense that this is then how people can be expected to behave in the auction, right? So they will probably use a Nash equilibrium, or at least hopefully. But the question is then, if you look at this Nash equilibrium, are people now doing what we hoped that they would do? And that is, from the perspective of the social planner, the question, do they act in such a way that the allocation is efficient? Because that is, after all, what we are after. And the answer is yes. So we can check that indeed we have what is called ex post efficiency. So given a realization, V1, V2 up to Vn, we know how people bid. And then the question is, do we allocate now to a person with the highest valuation? And the answer is yes. Why is that? Well, because we allocate to the one with the highest bid, right? So we allocate to a bidder I with Bi larger than Bj. But we know now that in equilibrium, right, that is under the Bayes-Nash equilibrium, so the bids are given by this formula. So Bi bids according to this, and so does J. And then you see that, in fact, these factors in front of the valuations cancel, and allocating to the highest bidder is the same as allocating to the one with the highest valuation, because they do not bid truthfully, so they do not bid their valuation, but they all use the same bid shade, the same fraction of their valuation as a bid. And that means that the one with the highest bidder, with the highest bid, is still the one with the highest valuation. So the auction does what we want. Okay, I think that is all I wanted to explain. And yeah, good luck with the exercises for this application. I'm trying to stop the recording, and I can do that here. Yes. So see you in the next recording.